Okay, so this section is about optimization. And this is actually probably something that you'll see most commonly in the real world. So, what we are going to be using this for is we are going to determine the absolute max or the absolute min based on some specifications. Okay, so a practical example would be I have a box that I'm using to mail out some items, and I want to change the shape of the box and maximize how much volume the box has. So this is really practical. Maximization. Maximization. Okay. All right. So these are word problems, and they do take a little bit of time to get used to how they all work. Okay. So what you want to do is you want to make sure you read the problem very carefully, identify any of your variables, and organize the given information with a picture. You're then going to identify the objective function. So this is our function that we are going to optimize, and you're going to write it in terms of the variables listed in the problem. You're going to identify any constraints. These are factors that affect the problem. Okay. You're going to use the constraints to eliminate all but one independent variable of the objective function. And then with the objective function, you are going to express that in terms of a single variable and then find the interval of interest for that variable. And then you're going to use some calculus to determine the minimum or maximum value of interest. So we're going to be using our derivatives again to help that. Okay. All right. So let's just run through some examples. And like I said, this is definitely something that's going to get easier once you go through a couple of problems. So you're going to need that time to practice and really get comfortable with this material. Okay. Okay, so for this first problem, we have two non-negative real numbers whose sum is 23. We want to maximize a squared plus b squared, meaning I want to make that the highest possible value that I can possibly get. And then I want to minimize what is the smallest that it could be given the constraint that my sum is, given that my sum is 23. Okay. So the first thing that we are realizing is that we have a plus b, the sum is 23. Okay. So what I'm going to do is I'm going to solve this for a. All right, so I'm going to get a equals 23 minus b. Okay. So my objective function in this case is a squared plus b squared. So what I'm going to do is I'm actually going to substitute in this value 23 minus b for my a. Okay. So I'm going to say there we go. All right, so I'm going to go ahead and FOIL this out, and I'm going to end up with 529 minus 46b plus 2b squared. 1b squared from my foiling, and then this b squared. All right, so what I want you to think about now is, since we had the constraint that a plus b has to add up to 23, that means the possible values for b in this case are going to be between 0 and 23. So that's my range. And I know that that is my range for B because it told me A plus B has to add up to give me 23. Okay, so then what we're going to do is we are going to take the derivative of the objective function to find the critical points. Okay, so let me write that down with a text. Take derivative of objective function to find critical points. Okay. Okay, and so we're going to use the objective function that we have substituted the value in so that we only have b's, okay? All right, so I'm just going to say f prime of b, because f is going to just be my objective function in this case, is going to be negative 46 plus 4b. Okay, so then just like we were working with before, to find the critical point, you're going to set this equal to 0. So negative 46 plus 4b equals 0. Add your 46 over, so you're going to get 4b equals positive 46. And if you divide by 4, b is going to be 23 over 2. Okay, so now what we are going to do is we are going to plug in our 3 points to our original function. So 0, 23, and 23 over 2. So when we're going to plug into, Chloe, we're going to plug into the objective function. So when b is 0, and we plug into our objective function, and I'm using the 529 minus 46b plus 2b squared, we're going to get 529. And when we plug in 23, we're going to get 529. And when we plug in 23 over 2, we're going to get 264.5. Okay, so what this is telling me is my max occurs when a equals 0 and b is 23, or kind of the opposite of that, when a is 23 and b is 0. So that's my maximization. My minimization is when a and b are both 23 over 2. And how did I know that they were both going to be 23 over 2? I simply just solved once I had B was 23 over 2, and I knew that they had to add to 23 over 2, what did A have to be to make that be true? Okay. And then that's it. Okay, so let's do another example. So in this case, we have an airline policy that states that the baggage has to be box shaped with a sum length, width, and height not exceeding 64 inches. Okay, so that is telling me that length plus width plus height has to be 64 inches or less, essentially. What are the dimensions and volume of a square-based box? And what would be the greatest volume under these conditions? Okay, so if we have a square base, we essentially know that my length and width are going to be the same thing. So in this case, I'm going to call them x. Okay. So with my volume then, we know that volume equals length times width times height. But since my length and my width are the same, I could say my volume equals length times width times height, which would simplify down to x squared times h. Okay? So the other thing that I knew from the beginning was that my length, my width, and my height added together had to give me 64. Well, since I know that my length and my width are both x, I could say x plus x, so in this case, 2x plus h is 64. So let's go ahead and solve that for h. And if I solve that for h, I'm going to get h equals 64 minus 2x. So then what I can do is I can substitute that in here so that I only have x's. All right, so x squared times 64 minus 2x. Okay, so before I FOIL this or distribute this out, I'm going to set each of these pieces equal to 0 to get my bounds for my x. So in this case, from the beginning piece, x squared, that's giving me a lower bound of 0. And then if I do 64 minus 2x equal to 0, I get 64 is equal to 2x. And I can divide by 2 to give me x is 32. So that is giving me my limit for my x is going to be in between, 0 and 32. Okay, so now I'm going to go ahead and distribute it out. So my volume is 64 x squared minus 2x cubed. Okay, so now I'm going to take the derivative because I need to find my critical points. So the derivative of my volume with respect to x is going to give me 128x minus 6x squared. Okay, so as you know, we're going to factor this and we're going to set it equal to 0 to find our critical points. So I'm going to say What can I take out from both of these? I can take out a 2 and an x. And that will leave me with 64 minus 3x. Okay. All right, so that's telling me that x is 0 or 64 minus 3x equals 0. So 64 is equal to 3x. Divide by 3. X is 64 over 3. Okay. So now we are going to test our 3 points that we have. We have 0, we have 32, and we have 64 over 3. Okay, so when you plug in 0 to volume equals, so we're plugging this into 64x squared minus 2x cubed. So when you plug in 0 for x, you're going to get 0. And when you plug in 32 for x, you're going to get 0. All right, now let's see the fun one. When I plug in 64 over 3. Okay, so this one's going to be a little bit messy when we plug it in, but you will end up with 262,144 over 27. And that is inches cubed. Okay. Okay, so that is the greatest volume that I could possibly have. So my dimensions for my x and my y, so my length and my width are 60, I said y. My length and my width are x, which is 64 over 3. So we can actually solve for our height now. Okay, so since we know that length plus width plus height was 64, and we know that both length and width are 64 over 3. Okay, so we can add that together and then subtract that from 64 to get my height. And in this case, the answer is 64 over 3. All right, so my dimensions are 64 over 3 for length, width, and height, and my maximum volume is 262,144 divided by 27 inches cubed. Yay! Okay, we have 2 more examples. So the last 2 examples are going to be a little bit more in depth. So we have a person in a rowboat that is 2 miles from the nearest point on a straight shoreline, and they wish to reach a house that is 6 miles further down the shore. The person can row at a rate of 3 miles per hour and walk at a rate of 5 miles per hour. Find the least amount of time required to reach the house, and how far should the person land the rowboat? Okay, so let's draw a picture to help process all of this information. So we had a house, right? And the house is on a straight shoreline. The person is in a rowboat. So, okay. And they are 2 miles from shore. So here's 2 miles. Okay. The distance from the shoreline, like directly to the shoreline to the house, is going to be 6 miles. Okay. Okay, so that's from here to here. Okay, so essentially, we're trying to figure out where should the person row to on the shore. Okay, so I'm gonna make this look like this. All right, and so I need to find out this distance right here, which I'm gonna call y, and this distance from just here to here, I'm gonna call this x. Now, if this distance is x and the whole thing is 6, I can find out this missing piece right here because it's 6 minus x. Okay. All right, so throwback to your science days. We know that distance equals rate times time. Okay. And since in this case we're trying to figure out time, let's go ahead and solve for t. So essentially we would just divide by r. So in this case, we're going to have our time is equal to our distance divided by our rate. Okay, so in this case, if you're thinking about this problem, the person in the rowboat is going to have to row for some length of time along this y distance. Okay, so the time that it's going to take the person to get all the way to the house, it's going to take y rowing that distance, and he can row at a rate of 3 miles per hour. So 3 miles per hour. All right, so he rows along line y, and then he's going to walk from this point here all the way to the house. Okay, so that distance there is 6 minus x, and he can walk at a speed of 5 miles per hour. Okay. Okay, so now we've got two variables. We've got x's and y's. So what we can do is, to simplify our life, we know that this is going to be a right triangle. And if that's a right triangle, I know that from Pythagorean theorem, x squared plus 2 squared is going to give me y squared. So I can solve for y. I can just take the square root. And in this case, I'm not going to care about the negative square root, because then that would be saying the distance of y would be negative and he'd be going backwards, and we're not, no, that's not going to work. So we're getting that y squared is going to be the square root of x squared plus 4. Okay, so now what we're going to do is we're going to substitute that in here for y. Okay, so we're going to get, switch back to orange. Okay, so t is going to equal x squared plus 4, all divided by 3, and 6 minus x, all divided by 5. Okay, so before I take the derivative of this, I know that the smallest amount of miles that the person will walk is 0. And I know the largest possible amount of miles that the person will walk is going to be 6. Okay. So I'm going to end up needing to take my derivative. So this one's going to be nice and easy because essentially the 6/5 is just going to go away since it's a constant, and I'm going to be left with negative 1x/5, and the derivative of that would be negative 1/5. Okay, so this is going to be negative 1/5. And then here with my t, I'm actually going to end up needing to do the chain rule. Okay, so I'm going to do that off to the side here, pink. So we know that u is going to be x squared plus 4. And then we're going to take the derivative of u, which in this case would be 2x. We have 1/3 u to the 1/2 is my original. So I'm going to multiply my 1/2 by my 1/3, and that's going to give me 1/6. U to the negative 1/2. And I need to multiply that by my du of 2x. So let's simplify that out. I'm going to get 2x divided by 6 square root x squared plus 4. And then you can simplify the 2x over 6. That can just simplify down to just having 3 in the denominator. Okay, so we're going to end up with x over 3 x squared plus 4. All right, so that was my derivative. Okay, so now what we're going to do is we're going to set this equal to 0. So I'm just going to go ahead and say x over 3 square root x squared plus 4 equals a positive 1/5. I'm going to bring that over to the other side. And then I'm going to cross multiply. So 5x equals okay. Divide by 3. Okay. And then I squared everything. So that gives me 25x squared over 9. I don't know about you, but I dislike fractions, so I'm going to multiply everything by 9 now to get rid of my fraction. Okay, so 25x squared equals 9x squared plus 36. All right, so we're going to subtract our 9x squared to be with our 25. So we're going to end up with 16x squared divided by 16. And again, when I'm taking the square root here, I don't care about the negative because we wouldn't have negative distance. Okay, so we have to test some points. So 0, 6, and 3/2. I'm gonna write this on the side, I think. Test. We're testing when x equals 0, x equals 6, and x equals 3/2. Okay, so when x is 0, and I'm plugging this into my t formula, I'm plugging it into this t formula in orange here. Okay, that's what I'm plugging into. So when I plug in x equals 0, I'm gonna get 28/15. When I plug in 6, I'm gonna get about 2.108. And when I plug in 3/2, I'm gonna get 26/15. Okay, so this is actually the smallest. So what that is telling me is that he should take your 6 miles and subtract out your 3/2, and that's going to give you 9/2. So he should park 9/2 miles from the house. All right, we got one more problem. All right, so we have an 8-foot tall fence that is running parallel to the side of the house, and it's 3 feet away. What's the length of the shortest possible ladder that is going to clear the fence and reach the house? Assume the vertical wall of the house and the horizontal ground have infinite extent. Okay, so let's draw a picture. So this one is going to have some similar triangles going on. So we have our house, and 3 feet away is our fence, and the fence is 8 feet tall. I guess I shouldn't have made it be that tall, because what we essentially want to do is make this look like 2 triangles. Okay, so it's a little bad picture. So here's my fence. Let me try to color code this a little bit better. Here's my fence, and my fence is 8 feet tall. Okay, and we are trying to find out the length of the ladder. Okay. Now, I'm going to label some more pieces on here. I'm going to call this B for the side of the house, and I'm going to call this distance from the fence to wherever the end of my ladder is, I'm going to call that X. Okay. All right, so the first thing that I'm noticing is I've got two sets of triangles, okay? I'm gonna color them for you. This right here in yellow, and essentially that's a right triangle, right? So I could say that b squared plus, this distance is 3 plus x squared equals the length of my ladder squared, okay? The other throwback to geometry days that you have is the fact that I've got this little smaller triangle here, okay? So in that case, I can say that 8 matches up with x. So I'm doing vertical over my horizontal distance. And if I say 8 over x for the green triangle, then I would say b over x plus 3. Okay? So let's go ahead and cross multiply this, and then we're going to solve for b. So I'm going to get 8 times x plus 3 equals b x divided by x. So b is there. Okay, so we're going to take and we're going to plug that in for b squared. Okay, all right, so okay, so this is looking a little cray-cray, but that's okay. So the first thing that I'm going to do to simplify this is I'm going to bring this squared into everything, but I'm not going to actually do anything out. I'm going to say 8 squared. I'm going to say x plus 3 squared, all divided by x squared. Plus, I'm just going to rewrite this one so it says x plus 3 squared instead. Okay, so now what I'm going to do is I'm actually going to factor out x plus 3 squared. Okay, so I'm taking this out from both of my terms, okay? Which means for me, I'm going to be left with L squared equals x plus 3 squared times 64 over x squared and 1. Okay. Okay, now, one other important thing to note is since L, which is the length of the ladder, is a non-negative, then L and L squared will have the same extrema, meaning we can minimize L squared. Okay. Okay, so that means we need to take the derivative of this. Woo, that's going to be fun. Okay, so I'm going to actually add another page after this. All right, so we are going to end up with okay. So we had L squared equals x plus 3. Just going to write the original on this page so we can have it to reference. Okay. So we're going to end up needing to do the product rule here. And I'm also going to have to do the chain rule for the x plus 3 portion of this. Okay, so one of the things I want to do first, though, is I'm going to change this to say 1 plus 64 to x to the negative 2. Chloe, I need you to not stand on the thing. Okay, that way it's just going to be a little bit easier for me to do the derivative. Okay, so let's do the first part. So for the x plus 3 portion, that's going to be my u. And so my derivative of my u is just going to be 1. So then we have u squared, and the derivative of that is 2u. We multiply that by du. So final derivative here is going to be 2 times x plus 3. All right, let's do the other side. So the 1 plus 64x to the negative 2 is going to give me a derivative of negative 128 x to the negative 3. Okay. So product rule. So remember, for product rule, you do the original times the derivative plus the original times the derivative. Okay. So I'm going to do the derivative of the first one, which is 2 parentheses x plus 3 times my original second one, 1 plus 64 x squared. I'm going to add that with my original first, so x plus 3 squared. Okay. Times the derivative of the second, which is negative 128 x to the negative 3. Okay. So let's write this out a little bit nicer. Okay. So we're getting 2x plus 3 times 1 plus 64 x squared plus x plus 3 squared. I should change it to a minus, shouldn't I? Yeah. I'll just leave it here right now. Okay, now, something that I want you to notice that we have in common here. Both of these terms have an x plus 3, and I can actually take out a 2 as well from here because this is an even number. So I'm going to factor out 2x plus 3 from both the first term and the second term. There we go. Okay, my pen picked a bad time to die. Okay, so we're going to factor out a 2x plus 3 from both the beginning and the end portion, which is going to give me, I think I'm going to try to type this since my pen just died. 2x plus 3 times 1 plus 64 over x squared. Oh, x squared minus 64 times x plus 3 all divided by x cubed. Okay, so I'm getting 64 because I'm doing 128 divided by 2 because I factored out a 2. Okay, so now what we're going to do is we're going to distribute in the 64 to this side. And actually, I think I'm going to try to keep writing, even though it's, let me see if I can get this pen to work again. Yeah, no, okay. All right, so I'm gonna have to do it with my mouse. All right, so now I have 2x plus 3 on the outside. And then it's gonna be more clear if I write it like this, 64 over x squared minus 64x. So now I'm distributing this here. 64x minus 192 all divided by x cubed. Okay, so now I need to make like denominators. And in this case, x cubed would be the denominator I want to try to make. So here I'm going to have to multiply my 64 by x to make that be x cubed. And I'm going to have to multiply my 1 by x cubed. So once I do that, I'm going to get 2 times x plus 3 gives me x cubed divided by x cubed plus 64x minus 64x minus 192. All right, almost there. Okay, so now I'm just going to simplify. So I'm going to end up with 2 times x plus 3 x cubed minus 192 over x cubed. Okay, So the next thing that I'm going to do is I'm going to set both of these equal to 0. So if I set this first one equal to 0, I'm going to end up with x equals -3. Okay, so is that possible? Can we have a negative ladder? No. Okay, so then for the right portion, I'm going to have x cubed equals 192. And then I'm going to take the cube root. Okay, and that is going to simplify down to x equals 4 cube root 3. Okay. So now what we're going to do is we're going to perform a test. So let me get another page. So we have our number line and we have 4 cube root 3. So we need to pick a number smaller than that. So in this case, I'm going to pick 5 for my test point. And then for greater than that, I'm going to pick 20. Okay, so I'm going to plug that in to my derivative. And if I do, I'm going to get a negative here, which means I'm decreasing. And I'm going to get a positive here, which means I'm increasing. Okay, so if it's decreasing and increasing, that tells me that I have a local min. All right, so since I have a local min at 4 cube root 3, and since this is the only min, it is the absolute min as well. Then what we're going to do is we are going to plug into the original to find L squared. And then once we have L squared, we can take the square root of it to find L. Okay, so we're plugging into my L squared formula. And if I do that, I'm going to get that L squared is approximately, oh, I wanted math, not miscellaneous. No, they don't have approximately. Okay. Okay, so it's approximately 224.77. Okay, so that's supposed to be approximately. All right, so then from there, I can take the square root of that to get what L is. And if you do that, you're going to get that L is about 15 feet. So the smallest possible ladder that I could have with the specifications is 15 feet. Okay. We have a rancher, and he's got 400 feet of fencing for constructing a rectangular corral. One side of the corral is going to be formed by the barn, so it doesn't require a fence. There's going to be 3 exterior fences and then 2 interior fences that are going to partition this corral into 3 rectangular regions. What dimensions of the corral are going to maximize the enclosed area, and what is the area of the corral? Okay, fantastic. So let's draw a picture because I like pictures. Okay, so we have the barn here, right? And then we have the fence. So these are my 3 outside pieces. So I'm going to call this distance X. which means this also would be x because it's rectangular. And then I'm going to call this distance y. Now we've got 2 interior fences that make this into 3 pieces total. So that would be like boom, boom. So I know that this is also going to be x, and this is also going to be x. Okay, so now it's time to organize my information. We have 400 feet of fencing, which means x plus x plus x plus x plus y has to be equal to 400 because that's how much fence I have. So 4x's plus y equals 400. Okay, now the other thing that I care about for this problem is the area of the corral. So we know that the area of a rectangle is going to be length times width, which in this case is x times y. So area is x times y. So you know we want to solve one of our equations to be in terms of one variable. So in this case, the 4x plus y, it's going to be easier for me to solve for y, since all I have to do is subtract 4x to the other side. So I'm going to end up with y equals 400 minus 4x. Okay, so now what I'm going to do is I'm going to take and I'm going to substitute that in to my area formula. Okay, so we're going to end up with x times 400 minus 4x. Now, before I FOIL that out, this right here is going to tell me that my 2 limits for my x. So I could have x equals 0 from this first part right here. So x could be 0, which really wouldn't make a lot of sense, right? But just work with me. Or we could say 400 minus 4x, set this equal to 0, which would end up giving me 400 is equal to 4x. So my upper limit for x in this case is going to be 100. Okay. All right, so now that we know that, we can go ahead and FOIL this or distribute this out so that we can find the derivative. Okay. Oops. So area equals 400x minus 4x squared. So let's take the derivative. So the derivative is 400 minus 8x. All right, so from here, we're going to find our critical points. And to do your critical points, remember, you're going to set your derivative equal to 0. So we're going to do 400 minus 8x equal to 0. So 400 is equal to 8x, divide by 8. And we're going to get x equals 50. Okay, so now what we're going to do is we're going to check our points. Okay, so this was finding the critical point. I just want to write that down. This was find critical point. Okay, and now we're going to perform a test. So we are going to be testing x equals 0, x equals 100, and x equals 50. okay? And we're gonna plug this into our area function that is solved for x, okay? So we are plugging this into a equals 400 x minus 4x squared, okay? So I'm gonna plug in 0, and if I plug in 0 for x, I'm gonna get 0. If I plug in 100, I'm going to get 0, and that makes sense because we set it equal, we set our original area function equal to that, equal to 0 to solve. And then we are going to plug in our 50. And if we plug in 50, we are going to get 10,000. Okay, so that tells me that when x equals 50, that's going to give me my max. Okay. So now that we know that x is 50, we can actually plug that in to find our y. So 4 times 50, and I'm going to plug into my original equation, 4x plus y equals 400, plus y equals 400. So we're getting 200. So I'm going to subtract that. Which is giving me that my y has to be 200 feet. Okay, so we know that x is 50 feet, y is 200 feet, and if we are going to find the area, we're going to do x times y. So in this case, we're doing 50 feet times 200 feet, which is going to give me 10,000 feet squared. All right,